The Newton fractal is a fractal based on the Newton-Raphson method. Newton-Raphson is a way of finding the approximate roots of polynomials and other functions. When this method is applied to functions of complex numbers, interesting fractal patterns are generated. This fractal wasn't discovered by Newton, it is named after him because of the Newton-Raphson method. Understanding the fractal needs basic knowledge of a few additional concepts. We need to understand the Newton-Raphson method itself. We need to know that real numbers, even positive numbers, can have complex number roots. And finally, we need to know how to differentiate functions of complex numbers, and by extension, how to apply the Newton-Raphson method to those functions. We won't cover these topics in great detail, just enough to provide context to understand the fractal. We will then look at some examples of Newton fractals. The Newton-Raphson method provides a very efficient way to find the approximate roots of a polynomial. Take this example polynomial function. We would like to find the approximate value of its roots. To use the Newton-Raphson method, we start by making an initial guess of where the root might be. The initial guess doesn't need to be very accurate. Let's make an initial guess of x equals 2.4 and mark the point on the graph. Then we draw a tangent to the curve at that point and find out where the tangent crosses the x-axis. In this case, we can see that the tangent hits the x-axis at approximately 2.1. We now replace our original estimate 2.4 with the new value 2.1 and repeat the procedure. We draw the tangent at that point and find out where that tangent crosses the x-axis. This time the new tangent hits the x-axis at a point that is even closer to the root. Repeating this a few more times will often lead to a result that is very close to the real root. We have drawn the tangents to illustrate the method, but in fact we can calculate the result without drawing anything. If xn is our current guess, we can calculate the next guess, xn plus 1, from this equation. xn plus 1 is xn minus f of xn over f prime of xn. Here f is the function we're trying to find the roots for, and f prime is the first derivative of that function. There is a link in the description to a video where this formula is derived. As we can see from the graph, the function crosses the x-axis in 3 places. So there are 3 roots where f of x is 0. Depending on our initial guess, the formula might converge on a different solution. For example, if we start with an x value of minus 0.4 and draw the tangent, this gets us closer to the root at 0. If we follow the Newton-Raphson process, it will indeed converge on 0. The Newton-Raphson method will often converge on the root that is closest to the initial estimate, but that isn't always the case. For example, see what happens if we start with an initial estimate of 0.48. At that point on the graph, the slope is quite shallow. The tangent hits the x-axis quite a long way from the initial position, where x is about 2.5. If we continue this process, it will actually converge on the root at 2, even though our start position was much closer to the root at 0. To try to get a better understanding of this, we can try lots of different starting points along the curve and see where each point converges. In this graph, we have marked the various starting points with a symbol to indicate where they ultimately converge. Starting positions marked with a red dot will converge on 0, those with a blue square will converge on 1, and those with a green triangle will converge on 2. This shows that the method will usually converge on the closest root, but there are a couple of areas where this will not happen. The small region of green triangles around x equals 0.5 will converge on 2. The small region of red dots around x equals 1.5 will converge on 0. As we will see shortly, Applying this method to polynomials involving complex numbers shows a similar effect to the one above. Certain starting points don't converge on the closest root. But in the complex domain, the patterns this creates are far more interesting. But first we need to look at the complex roots of polynomials. We will use an Argand diagram to show this. An Argand diagram represents a complex number as a point on the xy plane. The x position shows the real part of the complex number, the y position shows the imaginary part. We know that the square root of 1 has two possible values. It can be 1 because 1 times 1 is 1, or it can be minus 1 because minus 1 times minus 1 is 1. We can show these 2 points on an Argand diagram. What about the cube root of 1? We normally say that the cube root of 1 is 1. Minus 1 isn't a cube root of 1 because minus 1 times minus 1 times minus 1 is minus 1. But if we allow for complex roots, it turns out that minus a half plus root 3 over 2 times I is also a cube root of 1. This root is shown here with an x value of minus a half, the real part, and a y value of root 3 over 2, the imaginary part. If we multiply this number by itself 3 times, the imaginary terms cancel out, and the result is 1. So this complex number is a cube root of 1. The same is true of minus a half minus root 3 over 2 times I. This is also a cube root of 1. This root has an x value of minus a half, the real part, and a y value of minus root 3 over 2, the imaginary part. As you can see, all 3 roots are on the unit circle. They are equally spaced around the circle. The Newton fractal appears when we apply the Newton-Raphson method to find the roots of a complex polynomial, such as z cubed minus 1. Z cubed minus 1 has roots where z is equal to the cube root of 1. As we have just seen, there are 3 such roots. But how do we apply the Newton-Raphson method to a complex polynomial? We need to be able to differentiate z cubed. Is that even possible? Well, actually it is possible to differentiate certain complex functions, including complex polynomials. We won't prove it here, it is a large topic in its own right, but differentiating a complex polynomial works in exactly the same way as differentiating a real polynomial. We just replace the real variable x with the complex variable z, and apply the same rules that we use for real differentiation. This will be the subject of a future video. If you join my Substack newsletter, you'll be notified when new videos arrive. See the link below. If we differentiate x cubed, for example, we get 3x squared. If we differentiate z cubed, we get the same result, 3z squared, even though z is a complex number. We can apply the original Newton-Raphson formula to the complex function z cubed. We take the earlier Newton-Raphson formula and replace the real variable x with the complex variable z. So the formula is zn plus 1 equals zn minus f of zn over f prime of zn. This doesn't work for all mathematical functions, but it works for polynomials and quite a few other functions such as sine and cosine. If we substitute z cubed for f of z and 3z squared for f prime of z, we get the Newton-Raphson equation for the complex function z cubed. It is zn minus z cubed minus 1 all over 3zn squared. If we take any particular point z in the complex plane, we can apply the Newton-Raphson formula and find out which root it converges on. It will be one of the 3 roots we found earlier, either 1 or minus a half plus or minus root 3i over 2. This is what happens if we perform the calculation for different points in the complex plane. Each point is marked with a red, green or blue dot to indicate where it converges. The colour of each dot is the same as the colour of the root it converges on. Clearly most of the points are the same colour as the nearest root, meaning that most points converge on the nearest root. But it is also clear that some of the points converge on a different root. Notice there is also one solitary black dot at the origin where z is 0. At point 0, the first derivative is 0, so the next iteration of the sequence cannot be calculated. The point 0 doesn't converge on any route. This makes sense when you think about it. Point 0 is an equal distance from all three routes, and the system is symmetrical. It would be quite strange if the point 0 was to converge on one particular route, when all the routes are symmetrically distributed. The next step is to calculate the route of convergence at lots of other points. To create an image, we calculate the route for every single pixel in the image, and colour that pixel accordingly. Here is the result. This is the Newton fractal for z cubed. The structure is fractal in nature. There are three main areas in red, green and blue, but the boundary between these shapes is broken by a string of large teardrop shapes in contrasting colours. The shapes along the boundary between the red and green area are blue. The other boundaries also contain contrasting colours. Each of the large teardrops is bounded by smaller teardrops. Each of the smaller teardrops is bounded by even smaller teardrops. This continues forever. You can zoom in as far as you like, there will always be more detail. And the shapes are always similar, but not always identical. In this image, we have added an extra detail. For each pixel, we don't just check which route it converges on, we also check how long it takes to converge. Specifically, we check how many iterations it takes with the formula to get within 0.01 of one of the routes. The colour is made lighter for points that converge quickly, and darker for points that take longer to converge. This shows us that the points that are in the middle of a shape converge more quickly, but points that are close to the boundary of two different colours converge more slowly. This second image shows an alternative shading scheme. This time the colour only depends on the convergence time. It doesn't matter which route the point converges on, so the three main segments of the fractal are identical. We have used dark colours to show points that converge quickly, and bright colours to show points that converge slowly. This highlights the intricate shape of the boundaries between the areas. The fourth root of 1 has four solutions: 1, -1, I, and -I. Here are the four solutions on an Argand diagram. The roots are all equally distributed around the unit circle, but this time there are four of them. Here is a Newton fractal formed by using the fourth root rather than the cube root. It is also possible to create fractals based on other general polynomials containing multiple terms. If you enjoyed this video, please subscribe or join my Substack newsletter at graphicmaths.substack.com.